So the processor fundamentals, Von Neumann model 4.1.1, Von Neumann model. Remember, we also call it computer architecture or idea of stored programs. So early computers were fed data while the machine were running. It was not possible to store the programs or the data. That meant they could not operate without considerable human intervention. Think of a calculator. When you use it, you feed the data and then it works and then all it is gone. Neither your work nor the data remains. So in the mid 1940s, John von Neumann developed the concept of the stored program computer. It has been the basis of computer architecture for many years then. Remember, he just presented the idea, he wrote about it, and then his idea was taken by a couple of universities, they worked around it. He did assist them, but actively he never made the computer. The main previously unavailable feature of the von Neumann architectures were, number one, von Neumann architecture actually helps you to the processor, it was not there before him. Number two, processor can access memory directly. These are the features, all right? And computer memories can hold program and data together. That was the biggest feature. And the last, and that was most important, was actually the feature of stored programs. So stored programs, I told you that programs are basically collection of instructions. Means the program can now be written in the form of instructions and can be executed in order of the instruction. So the instruction, then instruction, then instruction, then instruction. All right. So what is the difference between data and program? Programs, when they execute, they take input, the process, and then they give out the data. So they consume data. While the programs are the collection of instructions. And data is what you give to the program as per the requirement. And then program processes. Now, few important things, the model itself. So let's suppose that this is computer's memory. Achha, let me make one thing very clear, that computer's memory is basically, whenever we refer to memory, we refer to actually RAM or the memory inside microprocessor. When I say the word storage, this is as per your syllabus, otherwise these are synonyms. When I say storage, so that means that permanent storage, where we can keep the data even when the computer is switched off. So get the idea. So hard disk, USBs and flash drives and external hard disks, so CDs and DVDs, they all are actually storage. And when I say memory, what I mean to say is RAM, or the memory, the RAM inside the microprocessor. ठीक हो गया? So let's make a representation of Von Neumann model, the pictorial representation of Von Neumann model. Okay. So now let's suppose that this is computer's memory. So let's suppose that this is computer's memory. All right. Memory as in RAM, random access memory, where we keep the data temporarily. Memory has got two parts in it. The address part, every memory location has got the address, and the data part. All right. So let's suppose that this is computer's memory. There we go. All right, and this memory hold few of the instructions. Remember the instruction when we are studying computer architecture, the instruction solely refers to the assembly language, So whatever the instruction that I'm going to write over here are neither pseudocode or any other language, but the assembly language, which refers to computer architecture. We will study assembly language. Assembly language is basically the part of this particular topic. So LDD, let's say 56, add 57, increase, and then store at 58, let's say, and then we have got end. What are these commands? How do they actually work? It is let's postpone it, we will discuss about it. So let's say this first instruction LDD 56 is placed at the address 50. This is 51. This is 52. This is address 53. This is address 54. All right. And then let's say we have got two more addresses, and then let's say we have got 56, 57, 58 as well. Let's say we have got 10 placed at 56, and let's say 19 at 57. Okay, so now what is happening, that I have depicted that how the RAM actually looks like. So if you look at the content, what is the content? This is the content of the memory. This content has two types. One is data, other is instruction. All right, the first one is data, the other one is instruction. Now, if you look at these two boxes which I have made from 50 to 54, you can see that these are instructions. How do we know these are instructions? Because these instructions are in English and they look like instructions. Like this is load, this is add, this is increase, this is store, this is end. Over here, we don't have any instructions, just the data. So this whole thing is instruction. Okay, so it looks like that this is instruction. So from address 50 to 54, these are instructions. And from 56 to 58, this is data. All right, so these are instructions and this is data. The whole thing is called what? Memory. The last thing that remains is this. What are these? These are memory addresses or memory locations. All right. So that is how your computer's memory look like at any given time, because it is only holding what? Program or their data. All right. So then comes microprocessor. Microprocessor itself is made up of many things. Okay. And those things are inside the microprocessor are called what? They are called registers. But microprocessor is made up of, apart from registers, it is also made up of system buses and system clock and other things. Let's first discuss the basics. Let's say we have got one register called program counter. Program counter register is basically a register which holds the address of next instruction. It holds address of next instruction. Okay. So what basically happens as soon as you click a computer's program's icon, that program gets loaded to the RAM. You know what is the meaning of word load? Load means that you are bringing the program or the data to the computer's attention. And how can you bring the program or the data to computer's attention? By bringing it to, or by loading it to the computer's memory. This memory is actually the part of microprocessor, but it is kept outside microprocessor for two reasons. First reason is that the size of the memory is a bit large. All right, larger than the processor. So let's say the processor is of the size of my little part of fingertip, maybe let's say 1/4 of my fingertip. Whereas the RAM module is bigger. So had they placed the RAM inside the microprocessor, the size of the microprocessor would have grown unnecessarily. So they kept it outside the microprocessor. The second reason to keep memory outside the microprocessor when it is part of microprocessor was the frequent need to upgrade memory. You want to change memory, you want to upgrade RAM. If I have got slower computer, the first thing that comes to mind is to upgrade RAM, because new programs, coming programs, what they do, they require more memory. So if the memory is full while the computer is running, the whole system becomes slower. All right, we will look into it as well. So for these two reasons, they keep the computer's RAM outside the microprocessor. But remember that RAM is not a peripheral. It is peripheral are those parts which are outside the microprocessor. They are not part of the microprocessor, but they are under the control of microprocessor, whereas the RAM is a part of microprocessor. So what if somebody comes to you and say that, have you done that? And let's say it's a surprise for you. You would say that, how would I know that I would have to do that? Nobody told me. If somebody would have told me, I would have done that. So this is what the case for your RAM. Until unless it brings to your attention, until unless it is brought to your knowledge that you have to do something, how would you do that? So similarly, if you want to make your computer do anything, execute anything, take anything from you, bring anything from the disk, you have to tell it. And how would you tell it? By having the program which actually makes the computer do this. And that program needs to be loaded. Now there are few words: load, upload, download. Load means that you are loading the program or the data from your local storage. Upload means that you are actually transferring the data from your computer's RAM to another computer's RAM. That is upload. That is not necessarily just this internet. This might be another computer in the same lab or same arrangement where your computer is, and these two computers are connected over, let's say, local area network, and you are transferring data from your computer to that computer. And does not mean that it is going to their hard disk or USB drive directly. Rather, it is being transferred. Download means that you are bringing the data from another computer's memory to your computer's memory. Let's say if you are watching YouTube. So YouTube server first loads that video to its RAM and then transfers that data through internet to your computer's memory. And then from that memory, the data is used and you watch the movie or whatever. So similarly, that is a download. All right, so let's say that you are actually accessing the DVD drive from another computer which is connected over the local area network in the same computer's lab where you are sitting. So that is downloading as well. So that particular computer is making use of its DVD drive, loading the data to its RAM and then transferring that data from its RAM to your RAM. Okay, so that is download. Whatever. When the word load comes up, it only means one thing, that the data or the program is brought to the notice of the computer so that computer could use it or execute it. All right. So when the program is loaded, let's say this is our program, a little chota mota program, which has got 1, 2, 3, 4, 5 instructions. Now the computer's memory is vast ocean. You never know that where your program will be loaded. You never know that. When at first the whole thing started, it was always the same because you had no chance of multitasking. Nowadays, when the program is loaded, you have no idea that where the operating system will load it. Since few people have got 2 GB memories, few people has got 16 GB memory. There is a vast difference between the amount of memories. These memories, as I said, that they can be changed. Their size can be changed. So where the whole program will be loaded, we don't know. Only when you ask the computer to load the program, operating system decides then and there where to load it. So operating system first looks for the empty memory and then loads the program. So it is not predictable that where the program loads. So if the program is loaded somewhere that computer does not know, computer cannot execute it. Like we are actually connected to our minds, computers are not connected to their minds as in memories, as in RAM. So operating system's duty is to tell the microprocessor where the current program which has just got loaded is present. So how would operating system tell? How operating system will load the program and the first instructions address. Let's say for this program, the first instruction address is 50. That 50 will be loaded to program counter. That is why I said that program counter holds the address of next instruction. So program counter holds the address of next instruction. Next instruction is always the instruction which will come up after this particular program. What if you interrupt a program and you load another program? So the current instruction would be of the current program which is being executed. The next instruction would be the instruction of another program that will be started execution. So this current programs which is just loaded, how would computer know? Computer will put the data inside the microprocessor. How? By putting this address of the first instruction which is just loaded to PC, and that address is 50. All right, that address is 50. So now the processor know where the first instruction is found. From this first instruction which is in PC, it goes to MAR, memory address register. Memory address register. Okay. So what is memory address register? Memory address register, MAR. It holds address of current instruction. It holds the address of current instruction. Which is current instruction? The instruction which is now being executed. What is next instruction? Which will be executed. So from PC, the address goes to MAR. So MAR now has 50, which is the address of the instruction which now requires to be executed, not the instruction itself, the address. But first we have to actually deal with one contradiction. The contradiction arises when program counter says that it holds the address of next instruction, and the memory address register says that it holds the address of current. When they both are saying two different things, how come they both are holding 50? PC says that it is holding the address of next instruction. Next instruction is 51, not 50. And MAR says that it is holding the address of current instruction. So current instruction is 50. So if current instruction is 50, PC cannot have 50. It should be a different one. So what basically happens that as soon as the address is transferred from PC to MAR, PC increments itself by 1. PC increments itself by 1. So PC will now become 51. All right, PC will now become 51. So PC increment itself by 1. PC will increment itself by 1. So now PC is holding the address of next instruction. Now you have to pay attention to this thing once again. PC always increment itself by 1. Because Von Neumann said that computers will be executing the program in the order of the instructions written. Means whatever the instruction that is written next will be executed. So by keeping that idea in mind, PC always increments by 1. If you want to change that order, you can, but by default, As soon as the address in PC moves on to MAR to become the current address, PC always increments itself by 1. There is no distinction to it. And for this reason, we call it sequential machine. Why do we call computer sequential machine? Because it executes the instruction in the order written, and that is always sequential, incremental order. So for this behavior of PC, we call computer sequential machine or serial machine. All right. So now PC address is moved on to MAR, and MAR address is now the current instruction. Now what MAR will do, MAR will actually connect with address 50. MAR will actually connect to address 50. Why it would get connected to address 50? Because we have placed, the computer has placed 50 in it. So with the wire that it gets connected to the computer's memory, the MAR, it is called address bus. Address bus. We call it what? Address bus. This address bus is responsible for taking address from the MAR to the memory or the other parts. So address bus. See, I have made arrow on one side. So address bus is unidirectional because there is no point. If let's say I want to make someone leave the seat and change the seat, I'll point out, hey, you get up from the seat and go to that seat. All right. So what I'm actually doing, I'm pointing out that you get up from that seat and go to another seat. All right. So I pointed out. So if I want to, I am the microprocessor, I want to access one memory location, I'm pointing out. Now what is accessing? Either to get data or to place data. If you want to take data from that memory location, you are pointing out that I need data from that location. If I want to put data, I'll be saying, go sit there, or I'll be saying, go save there. So in both of the cases, when the data is being fetched or placed, stored back in the memory, the MAR is always pointing out. Remember. So that is why we don't need the address to come back. Address is always pointed out. Okay. Now, how does this 50 reached out to the program counter? That is another bus. That is called control bus. What do we call it? Control bus. So control bus is actually not just for PC. It is actually responsible for other signals as well. Okay? So we will discuss about it later. So through control bus, the address of first instruction has reached out to PC. From PC, it goes to MAR. From MAR, it goes out to RAM as an address. Now, from that address, data or the instruction at that address arrives in MDR. So now it is MDR. MDR. Memory data register, MDR. Few of the books and websites also refer to it as MBR, memory buffer register. We'll talk about buffer later, but in short, the buffer is the area where we keep the data until it is get utilized. Once it is get utilized, buffer is then used for another data. So that is actually what is happening with MBR. So sometimes it is called memory buffer register, BR, but that doesn't make any difference as far as the purpose of this MDR is concerned. All right. So now what MDR is holding? MDR is now holding LDD, what? 56. LDD 56. This is now the content of what? MDR. Now you need to understand that this content is actually arriving from the memory. Do not think that it is arriving from the data part only. MDR is having the data from the address mentioned in MAR. Okay, so the bus, the wire that is being used to send the data is called data bus. All right, what do we call it? Data bus. Okay, so it is not bringing from the part which is actually the data part. It is bringing from the part of the memory whose location is mentioned in MAR. Now there is a general confusion. People do write like from MAR it goes to MDR. Nothing from MAR goes to MDR. MAR points to that memory location, and from that memory location you might have either the data or the instruction, whatever it is, whether the data or the instruction, that will arrive in MDR. That is the case. You need to mind it. Nothing goes from MAR to MDR directly. Rather, what basically happens that MAR points to a memory location, whatever the content at that memory location. We know that either we have the data or the instruction at any given memory location. From that memory location, whether it is data or instruction, that arrives in MDR. In this case, we are specifically talking about instruction. Do not think that this bus is actually going to this address or this bus is actually going to this address. These buses are going to the memory. That's it. Not to a particular address. Whatever the address that you put on that bus, the data will arrive in MDR from data using data bus from that particular location. So this is actually just for your understanding that it is pointing to it, it's bringing back, but do not think that it is actually physically going to that particular location. So get the idea? So from the MAR holds address 50, that address 50 holds LDD 56, that is actually arrived in MDR. Do not think that these are two parts. This is the whole memory. This is the whole memory. Okay. I just made these two parts distinct just to make you feel that these are instruction and this is data, but we know that in memory, anything can be at any location. So when MDR has got the instruction whose address was in MAR, that instruction from there now goes to another register which is called CIR. CIR. So what basically happens that the content of MDR, if it is instruction, it goes to CIR, and that CIR has now LDD 56. What does it have? LDD LDD56. Why does it have LDD56? Because from MDR it goes to CIR. It's a common behavior. Do not think that there would be anything else other than this. No, it's a common behavior. As soon as PC has got something, PC will deliver it to MER. As soon as MER has something, that will be placed on the bus. As soon as that address would be placed on the bus, bus will actually go to memory and will say that deliver the content of this address, and then computer would take the content of that address, in this case it is instruction, and place that over the data bus. As soon as that data bus has got something on it, that will be delivered to MDR, and MDR, if it is instruction, that goes to CIR. That is a common behavior. Now CIR, current, oh, we forgot to write the instruction, sorry, memory data register definition. So it holds instruction at address in MAR. So whatever the address that is in MAR, the instruction at that address will arrive in memory data register. And then we have got current instruction register. CIR. So what CIR does? CIR is actually current instruction registers. It decodes and executes the current instruction. It decodes and executes the current instruction. Decode and executes current instruction. You have to write current instruction, right? It decodes and executes current instruction. So the cycle is now completed. Once this happens, CIR decodes and executes. Again from PC, as soon as that is done, again from PC, 51 will arrive in MAR. PC will become 52, MAR now points to 51, add 57 will arrive in MDR, from MDR it goes to CIR, add 57 will be decoded and executed. Now what is decodation? Decodation is, like I said, let's say, my dear student, you bring me some water. All right. So you saw that I'm pointing at you. You will then decode what you need to do to bring me water. So all that understanding and execution plan that comes to your mind, that how would I go? How will I open the class door and I'll get out and reach out to that place where the water is. And then from that place, you will fill the glass up and get back to me to bring me water. So that whole thing that comes to your mind, and then you execute it. So decodation is actually making a sense of the instruction and how that instruction will be executed, and then execution. Fortunately, all you have to write is it decodes and executes. That's about it. You don't have to, neither here in AS or nor in A2, that how the decodation and execution happens. No. All you have to remember is just this cycle. From PC, the address of next instruction goes to MAR. As soon as it reaches MAR, it becomes the address of current instruction. PC increments itself by 1 in order to have always the next instruction address. MAR then points out to memory with the address in it through address bus. From that particular address, the content, which is the instruction that arrives in MDR, from MDR using data bus. And from MDR, it goes to PC, where the PC decodes and executes it. It is called fetch, decode, and execute cycle. What do we call it? Fetch, decode, and execute cycle. Now the part from PC to MAR to MDR, it is called fetch. So if somebody asks you what is fetch, you would say that address of next instruction from PC goes to MAR, MAR then points out to memory, and from memory that instruction arrives in MDR. And from MDR, it goes to CIR, that is fetch. And then CIR decodes and executes it. But there is a little more part attached to it. We will discuss about it. So now let's complete the microprocessor first. So what basically happens that this PC and CIR are part of control unit. They are now part of control unit. So what is control unit? Control unit is basically is something that reads an instruction from the memory. The address of the location where the instruction can be found is stored in program counter. Okay, this instruction is then interpreted. During the process, signals are generated along the control bus to tell other components in the computer what to do. The control unit ensures synchronization of data flow and program instruction throughout the computer. So what you come across few things. Number one, that this control unit is responsible for the fetch, decode, and execute cycle by having the address of the next instruction which will be executed. Okay, by having the address of next instruction will be executed, and then at the end, decodation and execution. Not just that, while the whole cycle is working, the execution, the order, the synchronization of the cycle and the parts in the microprocessor responsible for that cycle is also the duty of control unit. So it does synchronization. What is synchronization? Synchronization is that when a team is working, every member knows that from where to get the data and where to deliver the data and at what time. That is synchronization. So PC to MAR, then MDR, then CIR, that is synchronization. They work in order. Order requires some sort of timing. All right, so that order is also maintained by control unit. And then control unit has got this bus attached to it called what? Control bus. The instruction is then at the end is executed. Signals are generated along the control bus to tell other components in the computer what to do, because control unit is asking everything inside and outside the microprocessor, especially inside the microprocessor, through the control bus use. All right. So this was control bus. Sorry, control unit. Now, there is another part which is called ALU, arithmetic and logic unit. ALU, arithmetic and logic unit. Arithmetic and logic unit is supposed to be the hand of microprocessor. So whatever it does, the microprocessor, that actually the action part of it is basically happening using ALU. What does it mean? It means that control unit, like I am teaching you and I am writing everything using my hands. I'm fetching everything. If I'm having any work to do, I will do actually using my hands. So that hands to microprocessor is ALU. So anything which is logical or physical or whatever, that is actually ALU. We will talk about it later. So microprocessor's hand is what? ALU. Unfortunately, there is just one hand, so the speed is slow. But ALU is actually the hand of microprocessor. So ALU allows required arithmetic and logic operations. What are arithmetic operations? Addition, subtraction, division, multiplication. And what are logic? If, then, else, and application of and, or, not, nor, exclusive, or, gates. That is logic. All right. So if you have a statement if, then, else, then that means that logic part of ALU is actually dealing with it. And if you have got plus, minus, subtract, multiply, whatever, those all arithmetic operations are being done by the arithmetic part of the ALU. So while the program is running, this ALU is handling if, then, else, logic part, and addition, subtraction, division, the arithmetic part. It is possible for a computer to have more than one ALUs. You know, GPUs, the cards which are responsible for good gaming, all right, gaming cards, VGA cards, GPUs, graphic cards like GeForce, NVIDIA, and all, they are actually having more than one ALUs. We will discuss about it in detail later in AJUs. So it is possible for a computer to have more than one ALU. All right. So get the idea what is ALU. ALU is supposed to be the head of microprocessor. It does all the arithmetic and the logic when a program is being executed. So, and it is also possible that one computer may have more than one ALU. Over here, when the ALU is actually working, the data is being generated. See, if I ask you that what is the result of 1 plus 2 plus 3 plus 4 plus 5, you might say, sir, 15. This is actually very easy for you because your brain is actually quantum. Quantum means it can do several things together at the same time. You do quantum computing, whereas this computer is what? Sequential computer. I just told you that it does everything in sequence. It cannot do it quantumly. Your brain does it quantumly. So in sequence, it means that 1 plus 2, 3, 3 plus 3, 6, 6 plus 4, 10, 10 plus 5, 15. That is how computer does it. But you need to pay attention. 1, it should be kept somewhere in memory. Plus 2, 3, it should be kept somewhere in memory. Plus 3, 6, that 6 needs to be placed somewhere in the memory. And 6 plus 4, 10, that 10 needs to be placed somewhere in the memory. And then that 10 plus 5 is 15. So you need to understand that ALU, when it works, it requires a little memory every time, because if it does not have that memory, how would it actually go on with additions? So for that reason, ALU has got accumulator. Accumulator is actually a register which is used by ALU to keep the data. I call that data interim data, the data which is being produced during the execution and time, and the data which is at the end is produced. So what is accumulator? Unlike other registers which are special purpose means they only do whatever they are asked, whatever they are actually built to do. All right. Whereas the accumulator is temporary register, and it is used when carrying out ALU calculations. So it is a general purpose register. Rest of the registers that you have studied were actually special purpose. So these were special purpose. All right, from here until here, These were special purpose, whereas this accumulator is general purpose. General purpose register general purpose temporary register, temporary usage register that can be used by us as programmers, temporary in nature. All right. So that can be used by us programmers, by other microprocessors, whatever it is, accumulator, which is inside ALU, and it is being used by the ALU for the calculations during the execution of the program. So this is ALU now, which is having accumulator in it. Now, who is actually controlling this ALU? Obviously, there is one thing that controls this ALU, and that is control unit. So ALU is asked to do something by control unit, and the result goes to control unit as well. Okay, so the result goes back to control unit as well. And this accumulator and ALU, they are part of it. So ALU is actually controlling accumulator. All right. Now, this accumulator is having a link to arithmetic and logic unit, and then it has got another link to this accumulator to MDR. Now why? When the whole calculation is done, the result is found, the result is placed in accumulator, from where it will go out to memory. Until unless it is in memory RAM, we cannot access it. Whatever that is happening inside ALU is inside ALU. ALU itself is inside microprocessor. So we cannot access ALU or accumulator directly. So what computer does when it finds the result, it places the result in accumulator, and from accumulator it goes to MDR, and from MDR it goes out. You can see that this data bus is actually two-way. It is bringing in the data from the RAM, but it takes the data out from the RAM as well. So this is two-sided, but not two-way. This is single-way, two-sided. It is that alley which is in front of your home, and that is just one road. So if two cars are coming, one has to get aside to find the way for another car to get out of that choke. So get the idea. So it is actually a single way where the data is coming in and going out as well. All right. And when the instruction arrives, it goes to CIR, but when the data arrives, it goes to accumulator. So if the data is arrived, that goes to accumulator, which is being consumed for the next instruction or the current instructions work. All right. But sometimes the data is also required by CIR. So how would CIR access that data? That data will go to accumulator, and from accumulator, ALU will deliver it to CIR to work with it. All right. So get the idea. So this accumulator is directly connected to MDR so that the data could be delivered. Now, this was accumulator. This is general purpose register, which is being used for what? It is being used for accumulating the data while the execution of the program is going on. All right. Now there is another register called status register. Status register. This is something new for those who are actually coming from O level, because the status register is not part of the syllabus in O level. This status register is also under control of the ALU. This status register is also under control of ALU. Now what this status register does, it is also a general purpose register which is used for so many things. So it has got that thing that every bit of it is having a different purpose. Like in accumulator, you can place data. If you place the data, the whole accumulator is occupied. But in the status register, the different bits are used for different things. Like, let me tell you, if you do remember the additions, binary additions, there were carries and there were drops. So if there is a carry, one bit of the status register will be set. Means it would have one that yes, there is a carry. Similarly, if there would be a drop, another bit which is responsible for drop will be set. Otherwise, it will be reset. So it contains bits which can be set or clear depending on the operation. For example, overflow, the drop is overflow in the calculation, and the carry. There might be occasion when your program would have an error. That error would not let your program go any further. That is called execution error or program runtime error or whatever. Those errors, if they occur, there is a bit in a status register that will be set as well. So that this status register is also under control of, like accumulator, of ALU. So this is the status register. All right. There is another register called index register. This index register is used when carrying out index addressing operations. Addressing operations are what? Index addressing operations are when we want to access consecutive memory locations. Let's say I want to add data from 56 to 66, 11 memory locations consecutively. So I would be requiring a loop, as you would know loops. So in assembly language, for next and while are not there. So what we do, we use rather index address, right? So that addressing is used. So index register are also under control of control unit, all right, like any other register. So index registers are in control of control unit as well. We will discuss the working of index register exclusively later, but not now. Okay, now, so we have got index register, status register, CIR, and then we have got system clock. System clock. This is another new thing. The system clock is responsible for the speed of the microprocessor. System clock. All right. So this system clock is actually giving signals to control unit and arithmetic and logic unit. So what does this system clock does? System clock is used to produce timing signals on the control bus to ensure this vital synchronization to take place. Without the clock, the computer would simply crash Now, what is actually a system clock? You might have uh, heard of the speed of the microprocessor, 2 gigahertz. Giga means billion, hertz means billion cycles, means 2 billion instructions per second our processor can carry out, can execute. Let's say, this is just analogy. Later we would have a different version of it. So when this clock ticks, the next instruction starts getting executed. Faster the clock, faster the execution. You get it? As soon as this system clock ticks, the control unit starts next fetch, decode, execute cycle. You get that? As soon as the system clock ticks, ALU does next operation. So faster the clock, faster the computer. Slower the clock, slower the computer. Have you ever heard of this term, overclocking? Means that the company has set the microprocessor a bit under power. Under power means that it can perform more, but it is actually not performing to that level. So we can always go to BIOS setting and we can give it a boost by setting the speed to bit more than what is set by the company, and that is called what? Overclocking. But that overclocking's consequence is heat. So when computer works fast, there is heat generated. Anyways, so I hope that you got the idea of this. So this whole thing is called microprocessor. What do we call it? Microprocessor. We call it what? Microprocessor. So this is our microprocessor. Let's make it in a different color so that you have an idea. So this is whole microprocessor. Okay, so what microprocessor has got? Microprocessor has got system clock, ALU, index register, status register, accumulator, control unit, PC, CIR, MAR, MDR, oh, a lot of it. Okay. And this particular memory, RAM, is also called the part of microprocessor, but I told you that it is residing outside. So the main components of the processor are arithmetic logic unit, the control unit, the system clock, and the immediate access store. Now this is something new, immediate access store. IAS, immediate access store. Immediate access store. IAS. So now immediate access store holds all the data and programs that the processor needs to access. Now you can understand that what this immediate access store is actually. So it holds all the data and the program that the processor needs to access. The CPU takes the data and programs held in the backing store and puts them into the immediate store temporarily. What is backing store? Backing store is a storage, hard disk, DVD. This is done because read and write operations carried out using the IAS are considerably faster than read and write operations over the hard disk or the backing store. Consequently, any key data needed by an application will be stored temporarily in IAS to speed up the operation. The IAS is another name for the primary memory, which is actually what? RAM. All right. So IAS is actually what? RAM. Random access memory. So this is your RAM. Mind it. Immediate access store. The IAS holds all the data and programs that the processor needs to access. So you might have this question coming up. What is in the RAM? So you would say all the programs and their data which is being executed at the time. All right, so they all are actually there. Okay, so this is the constitution of the microprocessor. So do you know that how much have you studied? You have studied a lot. You have studied the formation of microprocessor. You have studied registers, special purpose and general purpose registers. General purpose, remember, status register is also a general purpose register. You have studied what is system clock, what is control unit, what is ALU, what is fetch, decode, execute, cycle, what RAM does. This is all the information that we need to understand the Von Neumann model and the system buses. Don't forget that. So let's take everyone one by one. Let's start with the what do we call it? The fetch, decode, execute, architecture definition. Hold on. Now see, Von Neumann architecture, if they say state, define, describe, what is, whatever, or they say Von Neumann architecture, computer architecture, just the architecture or idea of a stored program. In any of the cases, you have to tell them these four things. A basic computer architecture as described by the mathematician John von Neumann, also known as idea of a stored program. It describes a single processor composed of control unit, arithmetic logic unit, and memory unit. Yes, these were not there before him. Both programs means instructions and the data are in binary form and thus can be stored in the same memory. They are indistinguishable in the binary form, but still they can be kept in the memory. How they act upon it, we will discuss about it, but the short idea is that if you look at this picture, what do you see? If you see this LDD 56 thing, do you see that LDD 56 thing over here? This, it is one instruction, LDD, load directly from address 56. And these instruction and address are at different memory locations. This instruction itself is at 50 and this data is at 56. That means that this instruction now knows that where the data lies. no matter if this instruction is in the binary form or whatever the form, this instruction itself knows that where the data lies. So data lies at what? Location 56. So instructions themselves know where the data is. So as programmer, we don't have to be worried about it. As programmers, we don't have to be worried about it where the data lies. Instruction knows itself. All right. So even if they are indistinguishable, means they both are in binary and they cannot be seen and understood. If they are in binary form, doesn't matter. The instruction knows that where the data lies, so the instruction would access the data by itself. All right. So now, a single processor composed of control unit, arithmetic logic unit, and memory unit. Second is both programs or instruction and data are in binary form and can be kept in the same memory location, and they are indistinguishable in binary form. It uses input, output, and storage devices to acquire and store data in programs. So this should be data in programs. Before him, there was no storage. If there was no storage, means no stored program. If no stored program, you cannot program. If you cannot program, you cannot make general purpose computers, means the whole progress that is now that we have as far as the computers are concerned would not be there if he or Alan Turing would not have thought of it. It's a sequential machine. I told you that PC increases itself by 1. For that nature, it is a sequential machine because it executes one instruction, then the next, then the next, then the next, and it goes on and on and on. Until unless you deliberately change the instruction address. But if you change instruction address to another address in the PC, from that address onward, it would go sequentially. So this is a sequential machine. That is, it executes instruction one after the other and in the written sequence. And then we have got what Von Neumann architectures, fetch, decode, and execute cycle. This is what we have discussed. Von Neumann architecture, fetch, decode, execute cycle. From PC, the address goes to MAR. When I say goes to, it means that it is copied. Content from PC is copied to MAR. Then MAR with the address bus points to the RAM. Data from the memory address mentioned in MAR arrives in MDR. And that bus when points to the address from that address, content arrives in MDR and through the data bus. And in this case, the content is the instruction itself. Data from memory address mentioned in MAR arrives in MDR. From MDR, instruction is then copied to CIR. This is called what? Fetch. If the instruction has got address part in it, like I just have discussed, LDD 56. So 56 is what? Address part. Address part means that now the system requires the data from the 56 so that it could be loaded to accumulator so that it could be used further. LDD 56 means load directly from the address 56. We will discuss these instructions later. That is next lecture. So if the instruction that has arrived in CIR has got address part in it, if you would have noticed that there are two types of instructions that I showed, one that has got address in it, like these three, and one that has got no address in it. So there's no address in here, there's no address in here. So if the instruction has an address part in it, if the instruction in CIR has the address part in it, then it is copied to MAR so that the data from that address could be fetched. And the last one is instruction in CIR is then decoded and executed. As I said that you would not have to learn actually how the decodation or execution happens. All you have to do is to learn that CIR does it. So these two instructions are part of decode and execute. If the instruction is without address, it is simply decoded and executed. If it has got address, then that address will be placed in MAR so that the data from that address could be fetched and worked upon. So this is called fetch, decode, execute cycle. They will ask you to write about it. So now fetch, decode, execute cycle has got another form, which is called register transfer notation. This is same. This is sort of mathematical form of this fetch, decode, execute cycle. RTN, register transfer notation, is symbolic notation used to describe the micro operations between the registers. When the data is moving from register to register, these are called micro operations. So these micro operations, when they are described in symbolic form, like in mathematics, it is said to be register transfer notation. And I told you that it is actually another form of what? Fetch, decode, execute cycle. The term register transfer means the availability of hardware logic circuits that can perform stated micro operations to the same or another register. Like PC moves to MAR, MAR moves to memory, memory moves to MDR, MDR moves to CIR, and CIR is execution with the help of ALU and accumulator. So if they are connected and they are actually holding up each other for the work, and then they are handing the data and all that, that is all actually micro operations. So following is the register transfer notation to denote the micro operation performed during fetch, decode, execute cycle. Register transfer notation is something big. For your syllabus, it is just confined to fetch, decode, and execute cycle. So these two large brackets means the value, the content. So if there is a variable A is 5, so this means we are referring to 5. This thing means we are referring to 5. Mind it. Okay. But if I like write like this, so it means that I am generally referring to A. But if it is in the bracket, it means that I am referring to the value of A. They might look like the same, but in computer, these are two different things. Okay. So what does it mean? The content of PC. See, how the content has reached to the program counter is not our concern. This is not in our syllabus. So it is understood that whenever we discuss fetch, decode, execute cycle, we will start from what? PC. All right. So we will start from PC, and we will consider only what happens afterwards, not before that. So the content of PC is transferred to MAR. All right. And the content of PC is incremented by 1 and assigned back to PC. So we can say that the PC has incremented itself by 1. So let's say if it was 50, 50 plus 1 becomes 51, and it is assigned back to PC. So the content of PC is increased by 1. Now these are two brackets. Inside bracket, let's say MAR has got address 56. So when I say MAR and at address 56 in memory, let's say at address 56 in memory, let's say I have 100. Okay. So when I say MAR, I mean 56. When I say the content of MAR, I mean 56. But when I say the content at the address mentioned in MAR, then I mean 100. So inner bracket means the content of MAR, that is 56. Now 56 is taken. So at first stage, it will be taken like this, which is 56. At second stage, it will be taken like this. Whatever is at 56, that is 100. Mind it. So this is andar wala bracket, and this is bahar wala bracket. Get the idea? So the content of MAR is actually the address in the memory. The content of that memory address is then fetched and placed in what? MDR. In this case, it is an instruction. So content of MAR is memory address, and from that memory address, from memory, the content is fetched and placed in MDR. Means simply the instruction from memory, it has arrived in MDR. And the content of MDR, which is an instruction, goes to then CIR, and over here The bracket means that CIR decodes and executes it. That's it. So you would have to actually remember this in this shape. They might give you this as to write as a whole, or maybe in the form of blanks, or maybe they shuffle it and ask you to put it in order. Whatever, you need to remember all these 5 things. These are not no different than fetch, decode, execute cycle, and register transfer notation is only limited to fetch, decode, execute cycle in your syllabus. So the content of PC goes to MAR. PC increment itself by 1. The content at the MAR is the memory address. From that memory address, content arrives in MDR, and from MDR the content arrives in CIR. Then CIR decodes and executes it. Get the idea with it? Now, this is what you have learned, and now definitions. Arithmetic and logic unit, a part of microprocessor. It is an independent unit that takes its data from memory registers and hold accumulator register. It does all the operations and it works in sync with system's clock. Faster the clock, faster the work of arithmetic unit. ALU contains the logic circuit to perform mathematical operations like additions, logic operations like AND or and logic bitwise operations. Bitwise operations are those which we have done in additions, column by column by column. So that is bit by bit by bit. ALU is supposed to be the head of microprocessor. It does all the operation that it requires. Then we have got control unit. I'll be sharing these slides with you today. Do not worry. Control unit is a component of the CPU that directs the operations of the processor. It tells the computer's memory, ALU, and IO devices how to respond to instructions that have been sent to the processor. It is all of the steps performed during fetch, decode, and execute cycle are coordinated or synchronized, and completed by the register under the control of control unit. So without control unit, nothing could happen. All input, output, and everything. Fetch, decode, execute cycle, it is all happens using control unit. So system clock, a clock inside the computer that is responsible for the synchronization of all the internal components. That means they all do their work, and when the clock is high only. High only means that you see system clock goes like this, on, off, 1 second, and then let's say if it is 1 second cycle, 1 second has got so many milliseconds, so many microseconds. So clock does not go by second. So clock goes like on, off, on, off, on, off, on, off, on, off. So when the clock is on, only then system works. When it is off, it does not. So that off time is actually the time when the thing is happening. On time is when the system clock is saying that go on for the next thing. ठीक है, मैं आपको बोलूं कि जल्दी जल्दी काम करो, चलो अगले पेज पे आ जाओ, आपने जितना काम कर लिया वो आप कर लेंगे, फिर आप अगले पेज पे आ जाएंगे, फिर मैं आपको थोड़ा सा टाइम दूंगा, फिर बोलूंगा अगले पेज पे आ जाओ, ठीक है. सो अगली इंस्ट्रक्शन पे आ जाओ, ये बोलता होगा सिस्टम क्लॉक. So when the clock is giving time, it is off. When the time for the next instruction execution starts, it is on. So system works only when the clock is on. And then we have got instruction cycles. Instruction cycle and clock cycle are two different things. As I said that I just described one of the instruction, which was LDD56, means that load the data directly from the address 56. And then I said that in the execution part of the fetch, decode, execute cycle, that address 56 needs to be placed in MAR so that the data from that 56 address could be fetched and could be used by the microprocessor for the execution of this current instruction, which is LDD56. जैसा कि मैं आपसे बोलूं कि what is at page 9, so you would go to page 9 and then you will fetch what is at page 9 and then you will tell me. But the instruction is go to page 9 and fetch it. So you would have to go to page 9 to fetch it. So instruction cycle, It is a time period during which one instruction fetch from the memory and executes when the computer is given an instruction in machine language. So the whole instruction which is being executed is instruction cycle. Then clock cycle, the clock cycle is the time two adjacent pulses. Adjacent means on and off together, generated that set up the tempo of the computer processor. On off, on off, on off, on off. When it is off, the program is actually doing something. When it is on, next instruction. It is generally understood that the faster the clock cycle, along with other factors like bus width and the reasons for the better throughput of the computer, as only clock speed with other bottlenecks can be the reason for the faster microprocessor. What does it mean? What if microprocessor's clock, the system clock is faster, but the instruction requires, let's say, 3 or 4 things to do before moving on to next instruction? So 3 clock cycles will be used. If the instruction is requiring just 1 step to complete, then 1 clock cycle is required. If the instruction requires 2 steps to complete, then 2 clock cycles are required. So it means that faster clock is better, but it does not mean that in every single clock cycle there would be just 1 instruction cycle. Instruction cycle might be having 3 steps, so those 3 steps means 3 clock cycles. Instruction might be simple, instruction might be maybe complex. So if instruction is simple, it might go away in just 1 clock cycle. If the instruction is complex, it might go away in like 5 clock cycles. So faster the clock, better, but clock speed is not actually the measure for the faster speed of the program. In terms of time, it might be. In terms of number of execution, it does not. All right, so let's say we have got 4 instructions and all 4 instructions are simple instructions. So if they are simple instructions, it means that 4 clock cycles are good enough. So 1 instruction cycle is now equal to 1 clock cycle. But if these 4 instructions, out of these 4 instructions, let's say instruction number 3 is actually complex and it requires 5 clock cycles. So it does not mean that now the whole program will be executed in 4 clock cycles. It will require 1 clock cycle, 2 clock cycles, 6 clock cycles, and 7 clock cycles now. All right, so clock cycle is not a measure for how long the program will take to get executed. It might be a measure for the faster computer. All right, it's like a person can really run fast. All right, but what if you ask him to run uphill? Obviously the time, he would run fast, but the time will be increased now. All right, it does not mean that he has become old or he has no energy. Yes, he has energy, but down the task is complex. Get the idea? So his energy, his fastness, his rapidness is actually shown to us as best when it is in simple conditions, and it is shown to us as worst when it is complex situations. All right, so instruction cycle is the cycle which is for 1 instruction, the time that is required for 1 instruction, and the clock cycle is actually, clock cycle has no difference, it is always the same. But remember, instruction cycle, it only starts when the clock says so. So clock cycle is mainly used to start something and to go on with it, but instruction cycle is actually the instructions time that it will take. The instruction time that it will take will be counted in clock cycles. All right, so 1 instruction might take 1 clock cycle, 1 instruction might take 4 clock cycles, 1 instruction might take 3 clock cycles. All right, so IAS was the new thing. So RAM is actually, so whatever that is being executed and its related program, whatever is being executed and its related data is actually held up in immediate store Immediate access store is where the computer has to have everything so that it could take notice of it and use it. When computer requires anything, it looks into immediate access store. When it does it, when it completes it and it puts it back in immediate access store. And immediate access store is nothing but what? The RAM. Now, registers. Accumulator. I told you that it is general purpose register that holds the data produced during the execution of the program, the data that is arrived in microprocessor and yet to be utilized by the microprocessor, data, not the instruction. Data which will be stored back in the RAM and waiting because the address bus is busy. And if it, now there is one important thing that I need to talk about. If MDR, memory data register, has got instruction in it, then that instruction would go to CIR. But what if it gets data in it? Then that data will be transferred to accumulator. And then through control unit, that accumulator will utilize that data. Oh, that control unit will utilize that data in accumulator. But data doesn't go to CIR. CIR only have what? Instruction. So if instruction arrives in MDR, it goes to CIR. If data arrives in MDR, it goes to accumulator. Mind it. All right. Program counter. Responsible for the sequential execution of the program. This register holds the address of the next instruction. This is very important. So store the address of the next instruction to be read. All right, from the memory. Memory address register responsible for holding the address of the data or instruction to be fetched and written back to the memory. The instruction of data that has just arrived or going out will be first placed in memory data register. Mind it, memory data register is like the gateway of the microprocessor. Whatever comes in and goes out, it first stays in that gateway. That is the gate. All right, MDR. It is also called what? MDR. I told you that. All right. Current instruction register, it executes and decodes. Decodes and executes. All of the registers listed here, apart from the status and index register, are used in fetch, decode, execute cycle. Okay. Index register and status register are not used in fetch, decode, execute cycle. We will discuss about index registers later when we will be studying memory addressing techniques. A status register, let's see if I have, yes. Index register, mostly written as IX, and sometimes you might see it with IR, but in your syllabus it is IX. A value in this register is used as offset. Now, what is offset? Offset is actually displacement. Let's say if the address is 5 and displacement is 6, so 5 plus 6, 11. So this index register makes the address go ahead from the address which is base address. We will discuss about it. So let's just discuss at the time. Let's just discuss status register. And we will discuss about index register and base registers later when we will be studying memory addressing techniques. So status register is used when an instruction requires some form of arithmetic or logic processing. Each bit in this register is known as flag. So one of the bit in this register, this is a general purpose register and used to hold many different types of status during the execution of program. So that execution of the program is either the arithmetic or logic, because this is being used by arithmetic logic unit. I told you about it. Each bit of it is known as what? Flag. So flags are set and clear, set and reset, set and clear. Putting 1 is set, clear or reset is 0. So it has got carry. Carry is set to 1 if there is a carry following the addition operation that we have done. If it has got a negative flag N, carries C, N means the result of the operation is negative now in 2's complement. It has overflow, V. Overflow is called what? V. All right. So bit overflow is called V, carry is C. This is the name of that bit, particular bit. Then negative, I have not mentioned it over here, but we have got negative as well. All right. And then we have got zero flag. It is set to 1 if the result of an arithmetic operation is 0. So we have got zero flag Z as well. Which is Z, if the result of the operation is. And then we have got program error or comparison, error is E. There are different names of these bits, but this, think of it like a byte which is having different bits. Every bit is having a different operations representation, and this is called status register. All right. So we have got parity flag as well, and there are so many others, so just leave it out. So status register, as far as this the definition is concerned, this is a general purpose register used to hold memory, used to hold many different types of status during the execution of program, and that execution is actually nothing but what? Just the logic and arithmetic operations. And then the last thing that we have discussed today was buses. So Von Neumann architecture system buses. So control bus, this bus is a bi-directional, data can come in and goes out. So control unit use it to sync with all the parts of the microprocessor and outside. So this bus is a bidirectional bus and helps system to coordinate between microprocessor, control unit, and other parts of the system like main memory. This bus is responsible for carrying interrupt signals. We will study about it. Interrupt is part of Von Neumann architecture's topic over here in your syllabus, and device status. All right, and address bus. This is a unidirectional. I explained a lot about it. This unidirectional bus is responsible for carrying address to the devices for either storing data at those addresses or fetching data from those addresses. And then we have got data bus. This bus is used to carry data back and forth between the microprocessor and the other parts like RAM, IAS. So this is it, Bete. Thank you for being with me for that long. All right. So I have recorded this lecture